All right, how's it going today?
Fantastic.
Fantastic. Excellent. All right, so what I'd like to talk about today is the SLP, your ODPs, and Cs, so alphabet soup. Service Learning Project Proposal is due in a week, so I want to touch base on that and see where people are. I want to talk about ODP 404, 405, which opened this morning, and then some general comments on ODPs, and then we're going to start talking about C to get you ready for PA2, and then we'll loop back and we'll start doing some more Git tomorrow. So before I get into that, any questions up to this point? And I've got a fan going to hopefully keep the room cool. Let me know if the noise gets really bad, if it's a problem for anybody, come and talk to me, or if it's a good thing, because we're trying to find a solution to the heat in here, so we'll just work with it. So questions on anything?
Can I just ask a question about the ODP real quick?
Absolutely.
So I created an exception in my ODP that if you typed in nonsense for the second input, that it would.
Okay.
And when I tried assessing it that way,
Don't do anything that's not in the assignment. For PA1, PA2, you've got some creative liberty, right? The ODPs are graded by an automated system, so it's looking for an exact specification.
all right, that's it. Then I kicked it out and it worked.
Okay, cool, good. Yeah.
Would you like the SLP is more like a memo instead of us answering the questions in paragraphs?
I'd like sort of a standalone document. Okay, so like a cover page, service learning project proposal, your name, the date, maybe the title of your project, and then just start in with for my SLP, I am proposing, and so this is an outline, right? So project description will probably be your first section. The name, the partners, that kind of stuff can go on the cover page. And then, for my project, I'm proposing to build a solar-powered flashlight, right? And this will be great when it's dark because you don't need batteries for it, and you can go on from there. So something kind of like a lab report, but not with the sections you get in a lab report, but same thing, just sort of a standalone document that someone can pick up and start reading through, and they understand who you are, what you're doing, what your project idea is, the milestones, and so on and so forth. Yeah?
So you don't want us to include those?
No, I don't want this sheet turned in. I don't want you to just fill in some things in between here, right? I want a document. This is just an outline of some of the information I want. You can put other information in, and you can decide how much you need to say about each of these things. But project description should probably be, fairly extensive. It's enough to describe your project as far as you understand it and you've thought it out up to this point.
I just meant on the document, you wouldn't want
This page or those headings?
just those headings.
You could use those headings, yeah. You could have a section that says project description. But yeah, I'd probably have a section called milestones and then list, what the specific milestones are. So don't feel like you have to use this exact set of headings and such. But yeah, that's the information in there. And I'm not too worried about formatting and style and things like that. I'm mostly interested in content. But I always get some students who turn in a sheet of paper and in pencil they've scribbled a few words after each of these, and that's their SLP proposal. And that's not acceptable, okay? It's got to be a document. Like I say, imagine you're going to a venture capitalist and you say, I want $1 million because I got this great idea, and here, read this over, tell me what you think. Okay, so try to impress someone with $1 million in their pocket. Set the bar at that height. And you've got another week till this is due, okay? So the offer stands, right? We can iterate on this. Make a proposal or a draft of a proposal, go ahead and send it to me or come by and show it to me. I'll be happy to look at it, talk through it with you and say, this makes a lot of sense, but I don't understand this over here. Or you need to have some detail in this section, right? Don't do that the night before it's due, because I'm going to have 65 people doing that. Probably not going to get to everything. Okay, but you still got a week until the 10th, which is when it's due. So feel free to bounce this off me, and I can look at some of your drafts. Other questions? All right, so keep working on that. And remember, the goal for fall is really to get yourself to a point where at the end of fall, you have a really solid idea what your project is. Okay, your goal in fall is not to, you know, complete this and have a prototype and get your $1 million from a venture capitalist. Your goal is to come away with, okay, now I know what my project's going to be, and now I'm ready to start actually doing the work. So got an idea for a project, I do some digging into it, I'm gonna have to do this and that and the other thing to actually make it work, and you adjust your goals accordingly and so on, and over the next several weeks you basically refine the idea down to a point where you've got a pretty solid, stable proposal to start working on once this quarter is over. So don't feel like you got to do everything by the 10th. All right, so let's talk about ODPs. So ODP 404, I had some feedback from people having some questions. And again, if I get an email from you saying, I wrote my program and I'm not getting 10 out of 10, and that's the whole email, there's not a lot I can do with that. Okay, especially at 7 in the morning. If you send me an email and you say, here's my ODP, here's the code for it, right? I tested it as follows, and here's you running it 5 different times with 5 different test cases and seeing what the output is. And then you say, but I assessed it and I got 0 out of 10, and you show me how you assessed it and it says 0 out of 10. Now I know everything that you know about your question, right? And I'm not going to come out and say, oh, change this and it'll work, right? But I'll say something like, well, try this test case, right? Or maybe something simpler like, well, you assessed a different program from the one that you wrote, right? Or something like that. So I can give you more help the more I know about what's going on. So like we talked about the other day, do a cat on your file so I can see it in the output. Go ahead and show me your test cases. Go ahead and show me your assessment session, and then just use your mouse, select all of that. That'll copy it to your clipboard, go into the mail program, paste it in, send it to me. That I can work with, okay? The more information, usually the better. So ODP 404, the goal was not to write the word hello 5 times, okay? The goal was take 2 command line arguments, word and number, print word number times. So if I say script hello 5, it should print hello 5 times. If I say script goodbye 3, it should print goodbye 3 times. Okay? And I got some people who printed hello 5 times and said, I didn't get 10 out of 10, why not? So make sure it's doing what it suggests, right? And test the heck out of it. Okay? Test it with a number of 0 and make sure it doesn't print anything. It's an edge case. Edge cases are really, really important in programming. You write a program and it looks like it works great. You tested it and it worked, right? I said script hello 5, printed hello 5 times. That's the beginning of your debugging. Because it's the edge cases, it's the weird cases. It's when that first argument is blank. Script quote, quote, 5. It's when the second argument is 0. It's when the first argument's blank and the second argument is 0. Those are the things where it may break. Okay, and those are the ones that'll pop up, you know, a few weeks after your code's been deployed, and the customer calls up and says, hey, you know, my computer shut down this morning, what's the problem? It's some kind of edge case possibly, right? All right, so 405 is posted now. That's due tomorrow morning at 8. And here, we're mixing command line arguments and program inputs. So we talked about 2 ways of putting information into a program. Command line arguments are something like this. Program name, space, argument. Program inputs are where the program is already running and it says, hey, give me some input. And you type it in, hit enter, and the program continues and does something. And this ODP is supposed to be able to do both. So there's 2 things you can do. If you run the program with a single command line argument, which is assumed to be an integer, it prints out twice that integer. If you just say the name of the program with no arguments, it should print a single greater than sign, that's a prompt, and then wait for you to type in a number, hit enter, and then it prints twice the number. So I called my script try. So if I say try 6, it prints out 12. If I say try -6, it prints out -12. If I say try 0, it prints out 0. So there's a positive, negative, 0. That's a bunch of edge cases. But if I just say try, it prints a greater than sign, 1 greater than, no spaces, and it waits. And I go ahead and I type in a number like 98, and it prints out twice the number. Yeah?
So if you put, for instance, if and one or $1 is equal to true.
So if you want to know if there is a command line argument, your best bet is you could use $number to see how many you have, but if you want to check a particular argument, $1 equals equals, and then just 2 double quotes right next to each other with no space. But if you're going to do this, put your $1 in double quotes also, right? In fact, always put things in quotes if you mean them to be strings. If it's a number, don't put it in quotes. But if space, bracket, bracket, space, double quote, $1, quote, space, equals, equals, etc., then, and here $1 is missing. Yeah?
Theme, instead of the 2 equal signs, if it's a script, doesn't that have to be dash EQ?
For numbers, it's dash EQ. For strings, it's equal, equal.
Okay.
Because we also have dash LT and dash greater than and dash greater than or equal and so on. So that's how I remember that those are for numbers. Yeah.
So we output, when you do echo and then one echo bracket, automatically puts a parameter there, right? So how would I stop it from going to the next one and just put one
Echo dash N.
Okay. So it would stop it from going to the next one.
Right. So if I say right, so I'll say echo enter something, and then I'll read something from you, and then I'll just echo out what you entered. So that says enter something, and it just kind of sits there. And I say ha ha ha. And don't forget your number sign, exclamation mark, /bin/bash. Okay, the shebang in the beginning. It will probably work for you when you run this interactively, but it will not assess properly. Okay, so you want to make sure that you always have that as your very first line. Don't put comments before it. It's got to be first line. And always, always, always test your programs before you assess them. Okay, assess is deliberately not a way to test your program. It's just a way to submit it for grading. So you got to do all the testing yourself. And assess used to give you feedback, and it seemed like students stopped testing their programs completely. They'd write their code, they'd say assess, and that was part of their debug process. It's really not meant to do that. Okay, and it doesn't give you a lot of useful information. All right, so any questions on ODPs? All right, so let's start talking about C. Because PA2 is going to be basically PA1, but written in C instead of a shell script. There's going to be a few differences in how you handle errors, okay, but they're spelled out in the assignment. But it's going to be basically the same deal. So we need to talk about basic things in C. So let's look at your first C program, probably, Hello World. We can say hello world. I was trying to be original. All right, we'll say hello world. So that's probably the program that a lot of us started with, right? Kernighan and Ritchie, when they wrote their book on C in the 70s, this was the first program they talked about. They really introduced the concept of hello world to the world, and now every language, every hardware platform has a hello world. Okay, but that's where it came from, is Kernighan and Ritchie. So that's our C program, okay? And I called it hw.c for hello world.c. Does it have to be called something.c?
Yes.
It actually doesn't. Right? So, well, let's double check. Let's just call it haha. Oh, I'm wrong. Hey, that's weird. Okay.
Yes.
All right.
It has to end in .c.
Well, okay. So call it .c. So pure C compiler doesn't need it to be called anything in particular. All right. So it's got to be something .c. So what's this first line all about? We always write this, right? So we're saying include standard.io.h. What does that actually do, first of all?
Tell the compiler to like add the C, all the stuff for C.
Okay, it's adding some stuff for C, right?
Input-output library?
Input-output library, right? Because this lets us do things like printf and stuff like that. What happens if we don't include stdio.h?
We'd have to go to more,
We would have to define.
complicated alternatives.
Okay. We'd have to define what?
We would have to define everything that we do, like more specifically.
Okay.
Printf wouldn't work because there's code behind printf.
Okay. Yeah.
We use standard.io.h has a whole bunch of prototypes for functions. So
Right.
if we don't put that in, the compiler wouldn't know what printf means and it wouldn't know where to look for that function.
Okay, so yeah, that's a big part of stdio.h. It prototypes functions, right? Remember, when you write a function in C, you've got to have what we call a prototype, a description of the function name, types of inputs, the types of output, right? So that the compiler knows when you use that function what it should be passing to it, what it should get back. So what if we just get rid of this, right? What's it gonna do?
It'll probably screen on this.
It'll probably scream at us. Maybe it'll blow up in horrible fashion. So let's save this. No, I'm not on the server. Hold on. All right, so we compile it. We got lots of error messages there. Incompatible implicit declaration to built-in function printf. Include stdio.h or provide a declaration. So it's even telling us how to fix this, right? That's pretty good. But notice it says warning. Okay, warning is not as severe as an error. And in fact, it compiled hw.c and it gave us an HW. That's our executable program. And if we run it, it actually works. But don't do that. Okay? Warnings you should pay attention to and make sure you understand what the warning is telling you, and then decide, I understand that, I'm okay with it. Right? Or, I don't know why it's giving me a warning. Okay, stop there, go back in your code, figure out what the warning's coming from. Because it's risky to have warnings in your compilation and just keep going. But this will work better if we include standard.io.h. So no warning, and then it runs nicely.
So why was it still able to do the printf even without?
Because the compiler kind of knows about printf, even though it shouldn't, right? Which is how it was able to give us that nice specific warning about built-in function printf. So again, like a totally pure C compiler, right, doesn't know about these functions. It only knows what's been written in the program or what's in the include file. So it would just kind of like assume we were passing an integer, and it would probably do something really bad when you tried to run it. But today's compilers, right, they actually know some of this stuff that's most commonly used. So what actually happens when we include stdio.h? How does that change the behavior of this? Yeah.
It tells the program that we are including all the information on the prototype stored in stdioh as a valid resource library for anything we put in our main program.
Okay, good. So it's basically telling the compiler we're including information from this file, right? And it's going to be part of our program. Where is stdio.h? Where does it find that file? Did you ever look for it?
I had one before, I never found it.
So most of these come from /user/include. So /usr is sort of a top-level directory. It's like bin is where we store executable programs. Home is where we store our login accounts. USR is where we store various pieces of information, roughly. So if we vi/user/include/stdio.h, there's your include file. All 946 lines of it. And it's got, the copyright or the copyleft in the top saying this is Free Software Foundation. And a bunch of stuff that you rarely want to delve into because the people who write these things are not from this planet sometimes, and they do all kinds of crazy things. But if we dig down far enough, there's the prototype of the function printf. And it's some crazy stuff. It's got a ... It's kind of crazy.
Okay.
But that's the line of C code that stops that warning from popping up. So theoretically, we could put this into our program and not have to include stdio.h, except we'd need to include some other things.
Printf returns an integer?
Printf returns an integer, right? What integer does it return? Any way to find out?
Send a variable equal to it and find out.
Yeah?
Or echo printf, or print the return value,
Yeah, you could print it in a print statement any other way.
store it in a variable,
What's the lazy way that I would do because I'm lazy?
not too lazy.
Array.
How about the manual pages? Well, that's printf for one. We'll talk about the manual pages in a little bit. But here's a description of printf, fprintf, all of these different things. And they're usually pretty long and wordy, but somewhere it'll tell us about the return value. So return value. Upon successful return, these functions return the number of characters printed, including the null byte used and the output. All right, and let's talk about compilation. I kind of flew through the compilation of this, but I compiled it like this: gcc-o hw.c. So in 121, we probably just do this: gcc space name of the program. And when we do that, it creates this file with the weird name a.out. Right, that's our executable file. And we can say a.out, and it runs our code for us. But why a.out? I don't know, but it's not a lot of fun to type. So when I compile, I usually say, name the output file something, right? So -ohw says the output file should be called hw. But I could call the output file ha ha ha. Right, and now I've got a program called ha ha ha, and that's my compiled C program. So you can call your source code whatever you want, and you can call your executable program whatever you want. And that can help you organize your work as you're going and keep copies of your work and so on. Don't do this though. All right, what's this asking it to do?
Rewrite homework.c as an
Asking to rewrite hardware.c as or hello world.c as the output file. Now it's smart enough; it'll warn you that it can't do that, right? But you know, if for some reason you did something like that and you had an ODP 405.c, that's gone now. Okay. If you try to edit 405.c, it's just computer speak. Elf is always in there. I forget what it stands for, but it's in the beginning of executable files on Linux. So GCC-O, your output file name, and then the source file or source files. Okay, this is another reason to keep backups, because inevitably we all mix these up and we clobber our files. And so you want to go to your flash drive or your backup directory or something, get a copy. Okay, so what does integer main say? Why do we have to say integer main?
That's where the program runs, basically.
That's where the program runs.
It's the first place it looks, right?
More generally, when we say integer space something parentheses parentheses curly bracket, what are we doing?
We're defining a block of code.
We're defining a block of code, right? This is how we make functions in C. We say return type, function name, parentheses, list of arguments if any, close parentheses, and then a curly bracket. And everything from there to the matching curly bracket, that's the body of this function. And this is now something that we can call by saying function name, list of arguments, semicolon. So really all we're doing when we write our main program is we're making a function that's called main. Does it have to be called main? Let's call it my main. And let's compile it. It actually compiled successfully, but it did not build an executable program. And when you get error messages that talk about .text plus 20 or x86-64 and so on, those are not compile errors. Okay, even though this was a compile command, those are actually errors from trying to build the executable image out of the compiled code. So there's some things going on behind the scenes here. You write your source program, which is, file.c. And your goal is to get some sort of executable program. And I'll just call it a.out so we know we're talking about the executable. And typically we just say gcc file.c and we get our a.out. But there's things that happen in here. There's a step called compile. And this actually gives you what's called object code. The source code is this stuff, right? Which is arguably human readable. It's the stuff that we write, it's the stuff we understand what it is. The computer has no idea what to do with that. If you load that into the memory of a computer and you start executing it, the computer will probably crash. Okay, because this is meant for human ingestion, not machine ingestion. So object code is a bunch of ones and zeros that basically contain the instructions that the computer can actually understand. If you load those into memory and you start the CPU executing it, it'll probably do something more reasonable. But it still won't do things like printf, because printf is a function, right? It's the name of a function, parentheses, some arguments, close parentheses, semicolon. That's what we just said is a function call. We're calling a function named printf, but there's no description of printf in here. When I compile my program and I get object code, I'm only compiling the stuff that's in the source file. So this object code does not have a printf in it. I can't execute it. So I need to combine this with information like, what is printf supposed to do? Or what is square root supposed to do? So this goes through another step, which is called linking, to actually get, well, linking takes you down to the executable. There's actually another step in here that I skipped. When you compile your code, it does not go straight into object code. Your source actually goes into an intermediate language called assembly language. And that gets compiled into object code. And why is that? Because C is a standard language, right? Every C compiler in the world will know what to do with this program. Yeah, so there's a preprocessor before we compile too. So these things like number, sign, include actually get processed first. And then you get a big C program that gets compiled. But it gets compiled into assembly language. And I'll show you what assembly language looks like. So what I've done here was I put some switches on my compiler. -C says don't build an executable. Just go as far as object code. And -S says keep the assembly language file that you build on the way. So it created this file called helloworld.s, and this is assembly language. Okay, this is kind of like what you see in Engineering 270, except this assembly language is much more powerful than the PIC processor. But it's low-level instructions, right? Move long, move quadword, push quadword, things like that. And this translates into ones and zeros very easily. Okay, so the reason for all of this is the following observation. When we say GCC, basically all the stuff gets done for us. Okay, so we say GCC file, and it runs the preprocessor, it runs the assembler, it assembles the code into an object, it links everything in with the object, and it leaves you with an executable file. Right? But if we have a problem anywhere along that process, we're going to get error messages. So here the problem was we didn't have a main, we have a my main. It can compile that into assembly, it can assemble that, but when it tries to link into an executable, that's where it fails. And why does it need a main program named main? Because that's what the operating system will look for. Right? So we're not just making a piece of code in a vacuum, we're making a piece of code that's going to run on an operating system, i.e. Linux. And in Linux, when we say HW enter, what happens? The system looks for a file with the name HW. If it doesn't find it, it'll say can't find the file. If it finds it, it checks to make sure it's an executable file. If it is an executable file, it looks for a function named main. And if it finds a function named main, then it'll go ahead and it will basically start executing whatever code is in this function. But this is a fun and useful exercise to run through sometimes as you're doing different things on a computer, because we do these things all the time, right? It's useful sometimes to step back and say, how does this work, right? How is it that when I say HW enter, this is the code that starts running, right? How does that all get connected together? I had a student last year for his service learning project. He wanted to get into some hacking. So he was interested in ethical hacking, and he found a book called Ethical Hacking. Really, really fantastic book. And through the lens of seeing how different things are exploited in computers and computer design, he started learning about all of these kinds of details, like when you type in the name of a program, how does that code start executing? How does it get loaded into the memory? And if you've done 270, how does the program counter get pointed to that code so that it starts executing instruction by instruction? It's a really powerful thing to try to take apart and sort of break things down to that level. And it leaves you with a totally different understanding of what all this stuff is doing. And you've heard me say this before, if you're computer science, right, so we usually split electrical engineering and computer science. If you're computer science, you're not taking ESOT's 204 course and circuits and time varying signals and all that stuff, but you're not done with hardware, okay? Even after you finish 250, 270, the hardware is always there. And more, you've got to understand at least something about the hardware to be good at writing the software. Because long gone are the days when we write software and then we drop it into hardware and we just run it. It's all kind of integrated into a single whole. And the more you understand the hardware, the more efficient you can be at writing the software. And it works the same in the other direction. If you're doing any kind of computer engineering, you got to know the software side, even if you're a pure hardware person. So these worlds come together pretty seriously. All right, so that's the declaration of the main function. Printf, we've said, is a function. It takes an argument, which is a string, and it'll go ahead and print that string. And then what does return do?
Return in that case basically says return nothing.
Okay, well, return is 0, right?
Return is 0.
Which won't actually end up being the same as nothing, which is a weird
It
concept.
says that the block is done.
It says the block is done. So what do you think happens in the computer when that return statement is executed?
The operating system gets a value 0 return.
Yeah. In particular, we come back to the operating system, right? So there's always stuff running on here, right? When I'm sitting here and it's just kind of sitting here at a prompt, there's a program running, right? Do you remember what that program's called? Not quite Linux.
Shell script?
Yeah, it's bash, right? That's an actual program. In fact, right, that's the actual program. It's sitting under /bin. It's a little over 1 million bytes of code. It was last updated May 16th last year. It's just a big program. It's probably written in C. You can find the source code if you go online. And it's like any other program you would write in C. It says include stdio.h in the beginning. It's got some comments. It reads input. It does things, right? And this is a program running. It printed 1532, a space, and now it's waiting for me to type something in. It's doing an fgets or something. So bash is a program that's running in the operating system. And it's waiting for me to type something. And I type HW, and I hit enter. And it says, I don't know what HW is, maybe it's a program. So it looks for something called HW, it finds it, it checks that it's executable. And now it basically says, call that main program. So how many people here have done 270 already? Okay, if not, don't worry about this. But when you do a call, what happens? Assembly language, 270 flashback. What kinds of things happen?
Push into the stack.
Push into the stack. What do you push into the stack?
The address of the next instruction.
Yeah, the address that comes after the call. And then you basically start executing whatever this code is in main until you get to a return. And when you get to a return, you pop the thing that you pushed, which was the address of this instruction, and you jump there. So now you come back here and you start executing bash again. All right? It's the same thing that's happening here. It's the same thing we did in 270 with calling functions. It's just, it's a much bigger program that's calling and being called, but it's exactly the same concept. So this return 0 is saying go back to bash, all right? Because bash is the thing that called main. And the 0 is saying put that 0 somewhere, and bash is expecting a return value. So this would be like moving something to the W register and then saying return. And what does bash do with that return value? It makes it available to you in $? So we did this yesterday, but it's worth doing again, or 2 days ago. So if I return 17, and I run my program, it executes the code, it comes back. Now if I look at the value of $? It's 17, right? Because that's what my program returned. So it's not really like here's the operating system and here's my C program. It's all a big C program, right? I'm just adding a little new piece of it that's being called when I type in the name of this program. All right, everybody still here? So let's take this up a notch. Don't hate me. Let's put these things in. So you've seen these, right? Do you understand them?
I don't remember is it just int R, C, and the character R to B?
Basically. So this is one of these things that becomes kind of a mantra, right? When you write a program in C, you say integer main, parentheses, integer argc, comma, char star star argv, curly bracket. Or sometimes it's char star argv bracket bracket. There's different ways to do it. But we write this and we use it and we don't necessarily think a lot about what it's doing. We don't necessarily need to think through it very deeply. But let's do that. So when you run a program, we can say HW and it says hello world. What if I want to do something like, what ODP 405 is doing, but in C, HW, and I want to type some sort of argument after that and have my program do something with that 56. So the way you get to those arguments is using this pair of variables, argc and argv. So let's explore. Let's just do the following. Let's just print the value of argc. All right, so this is almost like hello world, but I'm going to take the value of argc, I'm just going to print it out as an integer. Right, so %d says format as an integer. And let's see what is going on. So I'll compile this up, I'll say hello world without any arguments, and it tells me argc is 1. I'll say hello world 45, it tells me argc is 2. I'll say hello world, this is fun, and it tells me argc is 4. So you got a theory now? All right, argc is the number of arguments, including the actual program name, which is why if I just say program name with no arguments, argc is not 0, it's actually equal to 1. Okay, warning, this is different from bash. Okay, bash, when you look at $number, it's actually the number of arguments. It doesn't count the program name. So if you say program name as a shell script without any arguments, $number is a 0. Okay, that's inconsistent with argc. Yeah?
If you do $0, do you get the program name in bash?
Yes. I forgot to mention that the other day. Thank you. So $0 gives you the program name in a shell script. All right, so argc is apparently the number of things we put on the command line, including the program name. What about argv? So we're going to spend some time later talking all about pointers, right? And we're really going to get into pointers in 222 in winter. But we'll touch on them a little more towards the end of this course and start to understand what we need to be able to use them in the next class. But this business of char ** argv. let's just take that apart a little bit. So if I say car star S, what does that mean to you? It's a pointer to a character, right? It's an array of characters. And we'll eventually make peace with the fact that arrays and pointers are the same thing, right? That's the odd thing about how C does arrays. But if it's a character pointer or an array of characters, that's also something that we're taught is a string. So it's a way to have a set of characters and say this is a single thing, this is a word, this is a name. And we declare it as car star. Now if we say integer star A, what is A? What kind of thing is it? It's definitely a pointer to an integer. It's an array of integers, right? So this idea of a pointer to blah is actually an array of blah. Okay? So one more, if we have a double star F, F is an array of doubles. So car star star argv, let me rewrite this. What is that an array of? It's an array of car stars. And car star S means S is a string. So this is an array of strings. There's a little bit of hand waving in there, but this basically holds together with reality. So 2 minutes left. Let's play with argv a bit. Argv, I've just said, is an array of strings. So let's print out the value of argv. So I'm going to print out in quotes argv0 equals %s, and I'll replace that with the value of argv0. And let's do hello world, this is fun. argv0 is HW. It's the name of the program. Oh, I messed up. All right, so let's take a look at a bunch of argv. So hello world, this is fun. argv0 is HW, the name of the program. Next argument is this, next argument is, next argument is fun, next argument is null. That should all feel pretty good until we go on to arg5, 6, and 7, which are strange things. They're not gibberish. They're stuff. But since argc is 4, we should only look at the first 4 things in this array, which are exactly the 4 arguments on the command line, the program name, and the 3 things that came after. And you should treat anything after this as suspicious. And in general, your program should never be looking at any of these things. Right? It's an array. Its length is 4, so it only has elements 0, 1, 2, and 3. And if you go beyond that, now you're probably going to get a seg fault somewhere. Okay, so we'll take that apart further at another point. But that's basically how we get command line arguments into our program, which is something you'll need to do for PA2. All right, so tomorrow we will talk about Git, and then Friday we'll talk about PA2, and we'll come back and start talking more about C programming and more of the structure of C code.